Hello, we are the hardware team for Passive Tactile Learning Gloves from Dr. Thad Sterner's Mobile and Ubiquitous Computing class. Passive Tactile Learning Gloves apply tactile cues to the user's fingers to help train the user to play piano songs. The motivation for building the Passive Tactile Learning Gloves is to train users to play piano songs in a short period of time. Built upon the core idea of ubiquitous computing, the gloves allow the user to learn the muscle memory using as little intention and effort as possible, as opposed to emphasizing or repetitive practice in conventional music training. The current prototype accomplishes this by using the glove's electronics to tap the fingers of the users for each note, but is basic and uncomfortable. Other challenges related to this project include networking and power. Our main objective is to improve the mechanical design of the tactile learning system through the implementation of a wireless synchronization algorithm to support a two-glove system and through a form factor redesign to enhance the comfort and dexterity a user experiences with the gloves on. To express the first problem of inter-glove synchronization, we propose using the precise time protocol over two Bluetooth modules, one in each glove.
We use the Tiny 0 as our main processor and a BLE shield for wireless communications, and also a proto board for any external connections. These boards can be connected together via the same socket, and we can use the Arduino IDE to program these tiny circuits. The example program is already uploaded. In this demo, we use an iPad as the master device of the BLE link. And I'll open up the serial monitor for any events from these tiny circuits. I will connect from the iPad and you see the event is detected. A wide range of services are supported, and for this demo I will be using the TX and RX UART services. I now enable the reception of incoming messages. I now send a message from the tiny circuit to the iPad, and you should notice the number changes. Next, I would send a message from the iPad to the tiny circuits. A string of 1010 is sent. And it is indeed received from the tiny circuit. Try a different string and it also works. Now I disconnect and that event is also detected. The next step is to program two of these tiny circuits with BLE shield, one acting as the master and the other acting as the slave. Then the synchronization algorithm will be implemented. We'll also use the outputs of the tiny circuits to drive the vibration motors with the help of Darlington circuits. It's currently being tested and we're able to drive LEDs. Later on, we'll expand it to more motors. We plan to use the PTP precise time protocol to implement the glove synchronization. It is based on two-way messaging between the two devices. More specifically, we will attach the timestamps of transmission and reception onto the messages, and the clock offset can be calculated and corrected as such. Here is our proposed solution. The two gloves, A and B, will each have a microcontroller and a BLE module. Glove A serves as the master. In the beginning, the vibration patterns of the sun are loaded onto both gloves. On start, A and B will synchronize, and A will initiate the song. Because of clock drifts, A and B will have to synchronize with each other periodically.
To address the second problem of usability and comfortability, we decided to first test and then break apart a tap keyboard prototype to get first-hand information regarding its fit and dexterity, and then gain insight regarding how the connections inside the glove made contact with the user. From this information, we drew several form factor sketches.
Finger pieces will come in 3 separate pieces. First off, the tap keyboard itself, in which each finger, and then there'll be the vibration motor and the finger-based motor controllers. This will effectively work by having the motor connected to the bottom of the tap keyboard or comparable device. This fits reasonably well on a finger in this form. With the wire will then loop up to the motor controller. They'll be on the top of the tap keyboard device. A method similar to this. Then, each finger will have wires connecting them in a manner similar to the way the strings currently already connect each finger piece.
This processor board provides power management, has built-in memory, and is Arduino compatible, all in a very compact size. The Tiny Zero processor board requires an external BLE or Wi-Fi shield critical for our implementation of two-glove synchronization. The Bluetooth Low Energy Tiny Shield will allow us to connect our Tiny Zero system to any compatible iOS or Android device using Bluetooth. It supports master and slave models, which is important in our synchronization algorithm, in which we will sync both gloves using the Precise Time Protocol, known as PTP. This protoboard brings out all Tiny Shield signals out to a point where we can easily solder to. It is stackable and the same size as the Tiny Zero processor board and the Bluetooth LE Tiny Shield. Darlington transistor circuit is ideal for interfacing with relays and motors to low-power microcontrollers and computer controllers. We are most hopeful in implementing Tiny Circuit's lithium-ion polymer rechargeable battery into our system. It has a nominal voltage of 3.7 and battery capacity of 290. Battery life is calculated to be around 4 hours. We chose this battery because of its small size and battery capacity, sufficient for longer usage and capable of integration into a thumb piece.